Okay, so we are going to be looking at the metal reactivity notes. And so for this one, I'm going to want to make sure that you have open, it says metal reactivity and I think EN polarity. Those are the notes you're going to want to have open, but we're only going to be looking at the first, the first page. So when it comes to metal reactivity, and this is what you're going to be looking at in the lab that we're going to do next time, it has to do with how well certain metals react with specific anions to make a reaction happen. And so in order to understand this, we're actually going to do a little Hollywood story here. So it comes down to Brad Pitt is what this story will be about. So over kind of to the side, on either side of this little chart that you have here, we're going to be taking some notes. So it started out with Brad Pitt. Wasn't he great? And he was married. His first wife was Jennifer Aniston. Remember, she was on Friends. It was really exciting. She had that Rachel haircut, and she was big stuff back in the 90s. And then they got a divorce. And Brad Pitt, I don't think they got married, but someone else walked into the picture, and that was Angelina Jolie. I'm just going to call her Angie for short. Angie Jolie. And so here they were. Brad and Angie, I think, met on the set of Mr. and Mrs. Smith. And Angie basically replaced Jen in the relationship. She moved in, and Jennifer was then left kind of out on her own. And so we had kind of a little rearranging. Then Jen was by herself. I'm going to bop down and just do initials now. And then we had Angie and Brad were together. And so to understand kind of how this relationship works and how it applies to chemistry, you have to think about celebrities as very kind of soulless individuals who don't have hopes or dreams, and we're just going to talk about them in a very, very superficial sense. So let's talk about the things that Jennifer Aniston has done. So Jennifer Aniston was on that Friends show, and that was big. That was really, really popular. And that's kind of it. Like, she did some movies that were very good, and she has great hair, but she's not particularly in the news very much for movies that she's done or things like that. On the flip side, let's talk about Angelina Jolie. So this woman is an Oscar winner. Most people forget that, but she won an Oscar for Girl Interrupted. So she's an Oscar winner. She was Laura Croft. That was exciting. Tomb Raider. She is a UN ambassador, a Goodwill ambassador, which is kind of a big deal. Let's see. She has poofy lips, great hair. She adopts lots of babies. So for the sake of argument here, we are going to refer to Angelina Jolie as very exciting. As a human being, this is the person you want to be around. Jennifer Aniston. Not exciting. She's very nice. I'm sure, again, remember, she's a very nice person, but we're just breaking them down to their stereotypes. So it turns out that the very exciting woman is the one who got to end up with Brad Pitt. And it turns out that you can kind of apply this story to chemistry in a very specific way. Just like Angelina Jolie is more interesting than Jennifer Aniston, certain metals can be more exciting than other metals. And so let's take a look over here at this chart that I've given you. This is called a metal reactivity chart, or sometimes called an activity series. And what this does is this puts the metals in order of most exciting, up here at the top, to least exciting down here at the bottom. So lithium is the most exciting and gold is the least exciting. These aren't all the metals on the periodic table, but these are the ones that we work with the most. So lithium up at the top, potassium, calcium, sodium. You saw we put sodium in water back in the fume hood and it exploded. The things down on the bottom are kind of boring. They don't do much. Copper, gold, silver, they just kind of sit there. So here's where that comes in terms of chemistry and how this Brangelina analogy is going to help us out a little bit. So I'm going to do this part over on the left side. So this is the Brangelina analogy and how it will help us understand what happens when we bring specific things together. The easiest way to do it truly is to just give you an example down here. So here we have magnesium plus AlCl3. So one thing that I'd like you to notice is if you take a look at this type of reaction, this setup here, this looks like a single replacement reaction. And that's exactly what it is. All the reactions that we're going to be looking at as relating to this Brangelina are going to be single replacement reactions. So kind of get your brain in that mode. And the thing to think about is when we bring magnesium metal into contact with aluminum chloride. Now let's take a look and notice the states here. Magnesium is solid. Aluminum chloride is an aqueous. So we're dropping a piece of solid metal into a solution. Maybe it's a beaker filled with that liquid, the aluminum chloride. So let's think about how this Brangelina analogy will help us predict what's going to happen. When we drop it in there, the magnesium and the aluminum are going to have a little battle. They're going to duke it out. The more exciting metal, and this is worth writing down, the more exciting metal gets the anion. Remember, the anion is the negative thing. They always come second in the formula. So in this case, the anion is that chlorine right there. So the more exciting metal gets the anion. How do we know which metal is more exciting, magnesium or aluminum? We take a look over at this. Let me do some erasing here. We take a look over at our metal reactivity chart. And it starts with kind of a little bit of a treasure hunt. First, you just have to find the metals. Here's magnesium. And there's aluminum. Oh, so they're right next to each other, but if you'll notice, magnesium is just a little higher than aluminum, which means magnesium has the ability to steal the anion from aluminum, and that's exactly what happens. So you can imagine here, magnesium is coming in for it. It's going to bond with chlorine, and then aluminum kind of gets kicked to the curb. It has to go be by itself. So let's think about how that would kind of rearrange itself. If we had, I'm going back down here to our reaction, magnesium is now going to bond with chlorine, and poor aluminum will be left all by itself to go star in Bruce Almighty. And so we're not quite done yet, though, because the very last part, just like we were working on with the most recent unit when we were practicing writing reactions, the last thing we have to do is figure out how magnesium and chlorine are going to come together. All we've said is that, yes, magnesium will kick out aluminum, but just because it's Cl3 over here doesn't necessarily mean it's going to be Cl3 when it's bonding with magnesium. The only way we can figure that out is taking a look on a periodic table. I find magnesium, and that's a 2+. Chlorine is a -1. So we crisscross those numbers, and we're left with MgCl2 plus Al. Now the very last part says to balance the reaction, and so that's what I need to do next. If I'm going to put, let's see, I'm going to do a 3 here, and a 2 here, and a 2 there, and a 3 there, and I think that ought to do it. So we have 3 magnesiums on each side, 2 aluminums, and 6 chlorines. Okay, so that was a case where the more reactive metal kicked the other metal out, and we had this kind of very, very fun, exciting adventure. So the next part has to do with maybe what if that doesn't happen? So let's take a look at letter B. Letter B down here, we have sodium and calcium are the 2 metals that we're going to be comparing. So the first thing you do is you go on a treasure hunt. Here is calcium, and there's sodium. So again, calcium is the more reactive one. So calcium, okay, so this isn't going to be an example of when it doesn't work, but I think the next one will. Calcium kicks sodium out, and it says, all right, sodium, you're going to the curb. I get the NO3. So that's what we see happen. If we were to rewrite these products, sodium is now by itself. Now notice I don't write any charge with sodium when it's by itself. I just write the symbol. I just write Na. And now calcium gets to bond with NO3. So that's happy, and calcium is very excited to be in that relationship. The thing, though, is that we need to figure out what formula these are going to make when they come together. So if you look on your periodic table, calcium has a 2+. NO3, that's on your polyatomic ion chart that has a -1 charge. So this formula, written correctly, would be Ca parentheses NO3 parentheses 2. And then the sodium is still there as well. So we can kind of erase this part. The very last part of that is I need to balance that reaction. So I have two nitrates here, so I need a 2 there, and then a 2 there in front of the sodium to balance. So letter A and letter B were both instances of where we add a really, really reactive, exciting metal, and it kicks the metal out of the compound. Let's take a look at a situation when maybe that wouldn't happen. So let's take a look at Al, Cl3, and Pb. The first thing you do with these problems, as always, is you go on the treasure hunt. You physically track down those metals on your chart. So let's see if we can find them here. Aluminum is right there, and lead is right down there. Okay, so in this case, aluminum is really much more reactive than lead would be. And if you look, aluminum is already in the compound. When we have a situation like this where the less reactive metal is already alone and the more reactive metal is in the compound, we say that's no reaction. No reaction would occur. We write NR. And so that's one where you kind of don't have to do any work, because if you mix those chemicals together, literally nothing would happen. There's nothing that we could do that could get that lead to kick aluminum out. That would be as if, letter C would be as if we had Brangie already together in a relationship, and then Jen came along, but nothing would happen. We would say that would be no reaction because Brad is already with Angie. So Jen, there's really nothing that Jen can do. She'll always kind of be by herself. All right, what I'd like you to do next is do the remaining 2 on your own. So letter D is CuCl2 and Al. Again, tell me if a reaction would happen, and if so, what products would you get? And then same thing down here, Mg and then SnCl4. Would a reaction happen? And if it would, what products would you get? And then bring this completed to class tomorrow.